to the Rich Report, a podcast with news and information on high-performance computing. Today, my guest is from Cycle Computing. We have the CEO of the company, Jason Stowe. Jason, welcome back to the show today.
Hey, Rich. It's good to be here. Thanks for having us.
Well, thanks for fitting me in. You guys seem very busy. I'm reading all the headlines about Cycle Computing this week. So, Jason, why don't we jump into it here? Why don't you tell us what's up with Cycle?
Well, we've been growing quite a bit, but we've also been starting to do some other large workloads, and I wanted to highlight one to you in particular that's a 156,000 core environment that we created. We actually benched it this time, so it has an R peak, not an R max, but an R peak of 1.21 petaflops. And we applied this towards accelerating material science in an effort to find more efficient solar panel materials.
Wow, that's what is that, like triple the amount of your last largest instance that you ever had?
Yeah, a little over a year ago we did one that was about 50,000 cores. Last February we did one where we didn't disclose the core count, but it was 10,000 servers. And this one is about 16 going on 17,000 servers and 156,314 cores.
Okay, so it's huge. Well, here, I brought your slide deck up. Why don't we go through that, and we'll do a Q&A at the end.
Yeah, sure. That sounds like a plan. Obviously, Rich, that we fundamentally believe that utility access to high-performance computing is going to be the single largest accelerator of human invention over the next couple of decades. So, my get up in the morning and go to work thought process is around how do we make it so that more people that didn't have access before can now ask, the right questions and be able to do high-performance computing, computational science at whatever scale is the right scale and not try to fit it inside the infrastructure that they currently own. So this is an example of a record-breaking run that we did. And if you go to the next slide, there's essentially on November 3rd, we ran what we're terming a mega run that did about 2.3 million hours of computing. So to give you an idea, this is 264 compute years. It's basically a little bit over a quarter of a compute millennium. And we operated essentially a 156,000 plus core environment that when we rated it using the Intel Impact benchmark, we basically rated every host as it came up as we were provisioning it and added those numbers together. So it's not an R max number, it's an R peak number, and got a 1.21 petaflop rating on this thing. And using that machine, we essentially were able to crank through the science in about 18 hours. So this is a huge workload. It ran on a very large compute environment that spans basically the entire globe. And the science is actually really interesting. So we essentially were running a simulation of compounds for organic photovoltaic cells. And the problem in solar is essentially an efficiency problem. So I'm going to, I know the Records Broken slide has a good overview, but I'm actually going to go to the challenge of material science, the next slide. So traditionally in material science, it actually took a long time to design, synthesize, and analyze an individual compound. Some grad students actually spend their entire PhD figuring out how to synthesize enough of an individual compound. And when you're done doing that, you don't necessarily know if it's actually going to turn out to be useful. So there's a heavy amount of risk involved with experimenting with new materials. So the total time could basically be, on average, about a year of a person's thought processes just figuring out how to even create enough of the stuff to experiment with it. And you're going to use hundreds of thousands of dollars in equipment to basically do that process. And the alternative, essentially, in this case, was using a Schrodinger material science tool set. So they have a suite of tools that can accurately calculate the properties of these materials in hours without you having to actually go through any of that effort. So it doesn't necessarily tell you whether how to synthesize the molecule, but what it does tell you is whether it's worth it right off the bat. You can do that computationally. And basically using spot instances in our software in this run, the time to enumerate the molecules, basically went from that year of grad student time down to minutes or hours for the enumeration and the analysis. And the cost is essentially 16 cents for infrastructure using AWS Spot instances. So it's a pretty heavy cost compression to analyze these materials before you even ever bother figuring out whether you could manufacture them. In designing the solar materials, if you go to the next slide, essentially the problem always with solar is material efficiency. So they want to be able to convert sunlight into electricity with as little waste as possible. And essentially the number of possible materials in this space is ginormous. And that's good in a lot of cases because it gives you a lot of flexibility. But in this case, it actually makes it very difficult to find the right material because there are so many different options. So essentially they need to separate out the right compounds from the useless ones. And as the researcher Mark Thompson that we worked with on this likes to say, if the 20th century was the century of silicon material, the 21st century will be all organic. And the problem is essentially how do we find the right material without spending the entire 21st century doing it? So the challenge for Mark, if you go to that slide, is essentially to find a more effective way of doing solar energy. So they're looking for materials that have a higher percentile efficiency of the energy coming in versus the energy coming out as electricity. And the challenge in this case was to screen a few 100,000 of these molecules. And we calculated that this would essentially be about 265 years of computing that we would have to do in order to screen this entire library of compounds using quantum chemistry. So the problem turns out to be essentially finding the right needle in the right haystack. Obviously, the researcher's intuition guides what families of molecules they're considering. But before, you essentially had to do the analysis and experimentation process on a really small number of compounds. And now you can essentially do far larger samples of more families of compounds and get a better analysis and a better result. So that's a big switch. And we think that, again, utility access. So, the run that we're talking about, if you had run it on a few hundred cores, would have taken 10 months to complete, on 300 cores in-house. And that's what an average material scientist kind of has easily available. But instead, because of utility HPC, we can actually do this, a lot more effectively, both in terms of the researcher's time, but also in terms of the cost as a whole. So if you look at some of the next slides, it talks about the reasons why utility HPC has been growing. And Rich, since I last talked to you, our customer base has gotten considerably bigger. I'm actually in Las Vegas this week at the Amazon Reinvent conference for AWS, and we've got Johnson & Johnson talking about data scheduling, which is another area of product that we've gone into. And we've got the Hitachi Global Storage Technology, which is a Western Digital company, talking about how they're designing next-gen hard drives on the cloud using our software. And the Aerospace Corporation is going to talk a bit about rocket design. They're the guys that put the man on the moon and Curiosity on Mars. And now their next rocket designs are being simulated on AWS infrastructure using Cycle. And lastly, we have Novartis talking about how they benchmark different instance types in order to do a very large run with them, the 10,000 server run that we did this past February. So there's a very large amount of interest and adoption of cloud. IDCs reported some very interesting numbers where the number of HPC installations that are doing any form of cloud or burst oriented strategy has gone up pretty significantly. It's now near 20 to 25% of the total HPC clusters out there, and that's a huge thing for adoption. And that's coming from a lot of the reasons that are on this solution slide. It's not just the capital efficiency of having OpEx versus CapEx, but it's actually the fact that we can actually accelerate research, accelerate invention because of this. And that's it's unfortunately a hard problem to date to do this, and this is one of the reasons why the adoption rate has been slower, but is accelerating over time. Is that basically it's very complicated and really hard to orchestrate technical applications in a secure way that's auditable at scale. And we've been doing this for a very long time and have a large number of users doing it currently. But that's really why everyone isn't doing this really on that next slide. So from a practical standpoint, we make software that tries to connect users with up to supercomputing capacity at their fingertips, and that's really what we do. So if you go to the slide talking about the challenge, in this case, what they're trying to do is a 205,000 compound run, totaling about 2.3 million hours or 264 core years. And what we did to solve this was we created a very large cluster. We used the Schrodinger material science tools to do the simulation. This is the quantum chemistry application tools that allow the material scientists to avoid having to synthesize the compound to determine if it's useful or not. Obviously, we used our software CycleCloud, and we used another new piece for Cycle, and this is something we wrote called Jupiter. Jupiter is essentially a distribution mechanism for tasks on the cloud. It's massively scalable, and it's very resilient, and I'll talk about it in a little bit more detail. And then lastly, we obviously used Chef as we have in the last several runs. It's a great way of deploying packages on this infrastructure. And we used AWS Spot instances to provide such a massive amount of compute capability at reasonable cost. So those are the tools that we were using. If you go to the next slide, essentially, this 264 core years, we did it with 16,788 instances. As I mentioned, 156,314 cores. And on the next slide, we talk about the rating for that. It actually turned out to be 1.21 petaflops, equivalent to the R peak of number 29 on the June 2013 list, which obviously will get updated this coming week. We're really excited to see where the new high water marks are for on-premise supercomputers. And the cost around this is basically about $33,000 for this entire run. So we used essentially $68 million in infrastructure for 18 hours and spent $33,000 on it. The average cost per molecule was about 16 cents, and the core hour cost was approximately 1.4 to 1.5 cents per hour. And this was a deployment, if you look at the map on the next slide, across all 8 regions that were publicly available. So we essentially were able to use capacity wherever it was located. And this is, again, because it's a pleasantly parallel workload. The individual pieces of this were actually small MPI jobs that used multiple cores on a single host. But the actual run itself as a whole was a high throughput job of all of these different molecule simulations. On the Jupyter scheduler slide, the next one, we talked about something, and Rich, I'm really excited about this. I unfortunately, we're not able to go into huge amounts of detail on it yet. We're going to publicly release this in 2014, but as a teaser, we decided to talk about a little bit about this for the first time with this run, but we've essentially written a task distribution mechanism that makes large cloud regions work together. It allows you to span multiple regions and data centers to resiliently route computational workloads with minimal scheduling overhead. So, in scale terms, it's essentially milliseconds, tens of milliseconds, fractions of a second, depending on the details of the configuration, from the task being in the queue to it being on a worker and executing. It also supports a service-oriented architecture. And, a lot of the batch schedulers and MPI schedulers that are out there are really good at getting, tens of thousands of cores to do, hundreds of thousands of jobs, maybe millions of jobs a day, but at any given point in time, hundreds of thousands of jobs in the queue. We really wanted to, obviously the supercomputers are really great at getting millions of cores to do one MPI job, the hero run that they're doing. In this case, though, we have a slightly different problem set. So what we need to be able to do, and this is because all of the new sciences are pleasantly parallel. So if you look at genomics, if you look at business analytics, if you look at robust engineering where they're doing CAD/CAM, each of the individual jobs is an MPI job, but there's hundreds or thousands of them. All of them are throughput oriented. And so what we needed is something that we could use to put together a very large amount of infrastructure, hundreds of thousands of cores, millions of cores, to do up to tens of millions of tasks. And what we're illustrating with this example on this cluster actually was a hundreds of thousands of core run doing millions of tasks at a time. So this is all done in a very scalable and resilient way as well. So it's a distributed scheduler, and one of the interesting parts about this is that it can actually survive Netflix style. And I don't know, Rich, have you heard of the Chaos Monkey?
No, I haven't.
So the Chaos Monkey is this little process that Netflix runs that constantly shuts down individual servers. They have a Chaos chimp that shuts down individual data centers, and they have a Chaos Gorilla that shuts down entire sets of data centers, so that they know their application is resilient, that Netflix will stream movies to you reliably. And this is just constantly running in the background, constantly every once in a while turning something off here, turning something off there to verify that the service is resilient. In this case, we could have actually survived any region, AZ, or individual machine level failure and still executed this entire workload. So we were essentially Chaos Monkey friendly. We were Chaos Monkey proof, if you will. And to show that, in the next slide, we actually have a graph of all the different regions in AWS. And I'm showing certain parts where we just flicked a switch, and based on the fact we weren't getting enough compute out of the cores in question, for the dollars we were spending on them in spot instances, we turned them off. So if you look at the far left rectangle, that's South America going away. If you look at the next rectangle over with the green disappearing, that's Australia being removed. So essentially, at various times, we were able to turn the lights off on an entire set of cluster nodes and still be able to run and execute the workload. And that's a really exciting feature for a lot of regulatory and deadline-oriented computation. So lastly, just some final facts and figures, and I think that's really all I got to cover, Rich, is we obviously did the math on the number of hours. It's 264, as I mentioned. We did 205,000 materials. It took 18 hours to do this. So this is the equivalent of, you're familiar with smallpox. There's a guy that cured it. His name's Edward Jenner. He cured it in the early 1800s, but he was born in 1749. So if you had started an individual Intel Sandy Bridge core the year he was born, it would have finished earlier this year, this entire computation. So this is before the U.S. even existed as an entity. That's how far back we would have had to have gone to execute this thing. And instead of finding a cure for smallpox, a lot of our runs are life science oriented that we've talked about in the past. This is actually more of a material science engineering run. So we're basically trying to find a compound to be a better clean energy material for solar panels. And then max scale is what I've mentioned, and essentially we're from a time to resolve on the next slide. If you look at it, if you bought a 300 core internal cluster using some of the numbers we've seen published around TCO from some of the analysts out there, and you gave that 300 core cluster to this user, it would take them 10 months to execute this 2.3 million hours, and buying the 300 core cluster in 2013 dollars, again, total cost to ownership. This is everything all in. This is the space for it, the processors, the data, the network connection, the admin to manage it, etc. And you're talking about 1/4 the price, and you get the result back in less than a day, as opposed to a little bit less than a year. It's a huge compression. So that's essentially it. And I guess I'll close with the last slide has a graph of the 156,000 cores. We also have some images of the chef converges, and I love showing these rectangle graphs. If you go to the next one, you can see, at the time we snapped this, there were 16,170 different hosts in the environment, 50 of which were having some problems or another that we were resolving automatically. But the fact that Chef can handle this is a really exciting thing. And we used all 8 public regions across AWS. So just as an illustrator, this is essentially what our UI looks like that shows you that information. And that's really the key of it.
Well, thanks for that, Jason. I guess congratulations are in order. This is quite a leap from just a year ago. Does the Jupyter, was that capability critical to making this possible?
Yeah, I think it really, if you want to be able to start approaching using hundreds of thousands or millions of cores that are dynamically provisioned, honestly, some of our test runs were larger than other people's clusters by an order of magnitude. So we had test runs for this run and for our software that were six-figure core count. It's not just the final run that hit that high. In some of our test runs, we would acquire 100,000 cores in less than half an hour.
Amazing.
As an example. So what you need is a software stack that's capable of understanding, rather than how do I spread this workload across this fixed amount of infrastructure that I have, instead it needs to understand how do I build the infrastructure to answer the queue that I currently am looking at. And we have a lot of IP and patent applications and what have you on essentially the opposite problem to what everybody's been traditionally solving. Traditionally, you try to maximize the use of the fixed-sized infrastructure that you jailed yourself into. What we're essentially doing is figuring out the playground that you need to actually answer the research question that you're asking. So it's the exact opposite problem, and doing that at very large scale is hard, and it just required us to build our own task distribution scheme. That being said, it is still designed to work well with other schedulers. So things like, for example, Grid Engine or Condor is actually really good in the cloud space because it deals with nodes coming and going quite well. It's probably the best batch scheduler when it comes to nodes leaving and being reintroduced. And essentially, our workers, the things that receive tasks and work on them, are designed to work with those traditional batch schedulers quite well. So in the meantime, it shouldn't be a difficult thing to adopt, number one. But number two, it should allow a lot of computational scientists to get some amazing science done, because scale is no longer really only for the people that have massive amounts of government funding or corporate resources.
To put that in perspective, Jason, there's only something like 35 supercomputers that have petaflop capability, and you've spun that up and put it to a practical use here from a worldwide set of data centers. I think that is just simply amazing, and it looks like a really practical application at the same time.
Yeah, we're really excited about it. I think, and I appreciate you saying that, Rich. It's one of those things where I think, from our perspective, when we release this software and in the early part of 2014, we'll have Jupyter out there. We're going to try to make it as accessible as possible for people so they can just use it. But I think there's a lot of good science. The thing that gets Cycle up in the morning every day is kind of pushing humanity forward on what we're doing and the questions we're asking. And I never, a day doesn't go by that we don't bump into the problem of someone's internal infrastructure being their bottleneck. They're thinking about questions that would could be answered on a reasonable time on the machines that they were able to afford to buy, at the end of last year with the budget money they had left over. It's that kind of situation. And that's exactly what you don't want your smartest people doing. You want your smartest people asking the big questions, getting the right things done. And it doesn't matter if it's 156,000 cores. Honestly, sometimes even having access to 16 cores that you don't have to wait, 4 weeks for your procurement cycle to give you, can do amazing science. So I do think the scale thing is important, but I also think that just the utility access model and knowing that, yes, I've got a secured way of reliably doing these clusters, that they're going to work. Every time I push the red button, I'll get it working infrastructure, and it'll be weeded out by the software for me automatically. Even at small scale, that's really useful. Most of our users are sitting between 40 and 4,000 cores, and although we do see, when we do these large runs, new sets of use cases come up that are big, and we expect that there'll probably be a lot of 30 to 50,000 core use cases that come up after this. I also think there's a lot to be said for small computational science.
Yeah, and I can't let you go without talking about resiliency because, as you know, Jason, the exascale computers we're planning are going to have millions of cores and threads and things, and that machine will constantly be in some state of failure. Something will be failing at any given moment, and computations have to keep going if that's going to be a useful device, and it looks like what you guys are working on here is a great leap forward towards that.
Yeah, I wasn't actually aware of that or thought about it around the exascale problem, but you're bringing up a really good point. I am curious to see how we're gonna. I've heard estimates that kind of towards the end of the 2010s we'll start hitting those scales, and I guess everything's going to have to move this direction because when you have that much processing power and that many hosts, it's going to be natural that something is in a bad state, which is exactly the situation we run into, when we're using this infrastructure on a regular basis. So yeah, that's a terrific point. And I'd actually, you're going to be obviously at supercomputing this year. I'd love to know if there's anybody that you guys are covering in the Rich report around, essentially that problem and the exascale problem. I should be paying more attention to that. It seems like.
I'll keep my ears perked up for that. So Jason, before I let you go, I did want to mention I kind of modeled you and your company in my recent sci-fi story. So you'll have to. I know you haven't read it, so I won't put you on the spot there. But this really is inspiring stuff, and congratulations.
Well, thank you so much, obviously, for thinking of us when you were writing. I hope we don't die a horrible death in the end. But,
well, I don't want to give it away. Well, anyway, Jason, congratulations on this, and thanks for coming on the show today.
Rich, thank you, and thanks for pointing out the exacycle stuff. I think that's a really important. Exascale computing is definitely going to be an issue. So thanks a lot.
You bet. Okay, folks, that's it for the Rich Report. Stay tuned for more news and information on high-performance computing.